Good, how about you?
Good. So what good challenging stuff do you have for me today?
Continuous extensions.
Okay. A PNG file. What kind of a file is a PNG file?
I have no idea, I just took a screenshot.
That's what your camera takes?
I guess so. Since I just screenshotted using the iPad.
Uh-huh.
And 43.
All right, let me look at this. I didn't quite know what you meant by extensions. Ooh, I'm still not sure I know what you mean. Well, we can figure this out. So 43. X squared minus 1 is the function when x is less than 3, and it's 2ax when x is greater than or equal to 3, and they want to know where it's continuous, or what value of a makes it continuous, right?
Yes.
Well, here's 3. And it's x squared minus 1, which looks like this.
Parabola.
And I stop it right there. And then the other function is linear, 2 times a times x. So that's going to do something like, let's draw it like this. And the only way that this entire function would be continuous is if the second function is equal to the first function at that point. You see why? In other words, what if the second function, the dotted line, hold on. What if the dotted line did this? Oh boy, let me draw it in a different color. And it ended right there. And let's see, that's a greater than or equal, so that would be the closed dot. Now, would that function be continuous for all x?
No, it wouldn't.
No, it wouldn't be right there, right?
Yes.
Okay. So what they're saying is what value of a makes the first function lie on the same point that that does. In other words, that's a closed dot there. So if that was our picture, we'd have a continuous function. Well, how do we figure that out? We let x squared minus 1, the function on the left, equal 2ax at x equal 3. So all I have to do is plug in 3 for x, and I get 3 squared minus 1 equals 2a times 3, and that gives me 8 equals 6a, a equals 4/3. So if a equals 4/3, then these 2 points will coincide when x equals 3. That's what we need, is for them to be in the same spot.
Okay.
Huh. Interesting way to describe it. Extends. Believe it or not, in 8 years of tutoring, I have never heard that expression.
Really?
Yeah, it's actually kind of interesting because I've always I had a Russian student, a kid who came to college here, but he went to high school in Russia. And I was curious as to, do they teach math differently in Russia? And he said, no, basically they teach it the same, but there was kind of different terminology. And this is not that you're in Russia, you're in Florida, but different than Colorado. So 44, for what value of b is the function continuous? Well, what do I need to do without drawing the picture?
-2.
So x has to equal bx squared when x is equal to -2. Okay, so -2 equals 4b. b equals -1/2. It's really as simple as that.
Okay.
45, tell me how to do
it. For 45, I'd just substitute 2 in for x.
So tell me what equation I need to write.
So I'd write x equals 2.
Okay.
At the top.
And then what has to be true when x is equal to 2? Let's write it in general before we substitute.
Okay, so a squared x minus 2a
equals
2 or 4.
12. 12. In other words, the top function and the bottom function have to be equal at x equal 2. Otherwise, it's not going to be continuous. Otherwise, there'll be a jump discontinuity at x equal 2. Okay, so now what's the next line I can write?
A squared times 2 minus 2a equals 12.
And help me solve that.
So I would do, okay, since there's a squared, so I'd take a, or I'd take an a out of the left side.
No? Here's what I want you to realize. When you see a quadratic, this is a quadratic. I have an a squared, I have an a, and I have a number. That's always a quadratic. You always solve quadratics by putting everything on one side and 0 on the other. So it's 2a squared minus 2a minus 12 equals 0. You can't solve it any other way. I could try factoring an a out. That won't get me anywhere. Okay, unless you turn it into a quadratic, I don't know of any way to solve it. And in order to turn it into this quadratic, you have to recognize it immediately. It's a quadratic. Okay. Now, there's one further thing I can do to simplify this before I try to factor it. What is it?
Take 2 out of everything.
So if I factor out the 2,
a squared minus a minus 6.
And now notice that I can divide both sides by 2, and I get this equals 0. And this is much easier to factor than that was. It's always easier to factor when your squared term has a coefficient of 1. Not 2, not 3, not 4. Anytime it's other than 1, it's a difficult factoring problem. But when it's 1, it's really an easy factoring problem. Okay? How do you factor that?
I'd put 2 a's in the front, and since it's a negative and a negative, it's going to be a plus and a minus. So I'd say -3 and a +2.
Very good. I even like the way you did it. You did it exactly the way I teach it, which most students don't care for because it's not the way any of their schools teach it. But to me, when you're dealing with a simple quadratic, which is one that has a 1 in front of the squared term, this is by far the easiest method to use. So what are my solutions? A equal what or what?
-2 or 3.
Okay. Now, for what values of A is that true? Well, both of those, -2 or 3, makes this thing true. Or excuse me, makes the top function equal to the bottom function. And that's what we're always doing in these problems, is we're trying to set the top function equal to the bottom function whenever it's at the value that separates the two domains. So how would I do 46?
Okay, so I'd write out x minus b over b plus 1. Then I would do 0 minus b over b plus 1.
Well, yeah, you're getting a little bit ahead of me. I would almost prefer to see you write it this way, because that recognizes the fact that you know this top function has to be equal to this bottom function. And where? When x is equal to what?
0.
Okay, so now when we plug in x equals 0, what do we get?
0 minus b over b plus 1 equals b.
Okay. Solve that.
Can I cross out the two b's on the left or no?
No, you cannot. No, you cannot.
Okay.
In other words, I could divide top and bottom by b, but if I divide bottom by b, I got to divide both terms by b. Okay? So that actually would work. It wouldn't, it's not that bad, but that's not the way you solve this typically. Excuse me, I got b over b plus 1. Solve any, you got one variable here, one equation. Start following a pattern.
Multiply b plus 1.
Get rid of the denominators, right? Get rid of parentheses, denominators, and exponents. Well, we only have a denominator, so how do I get rid of the b plus 1?
Multiply both sides by b plus 1.
Okay, now what?
Then I could, add the b to the other side.
Yeah, leaving 0 on the left.
Equals b squared.
Plus 2b. Now,
Oh, yeah.
this is a quadratic, but it is missing the constant. But that's okay. I'm going to solve this problem exactly the same way. It's a factoring problem. So how do I factor that?
I would have a b on the left and a b on the right.
Well, it factors in, it's a greatest common factoring problem. In other words, it's not a typical quadratic factoring problem, which are tough. This is easy. This is just taking out a greatest common factor.
B plus 2.
What is that?
B plus 2.
Uh-huh. Now what's the solution?
-2.
There's another solution that everybody forgets.
And 0.
Yeah, everybody never wants to consider that one. I'm not sure why, but those are your two solutions. It's kind of interesting that most people do not want to let b equal 0. So let's see, 47 next?
Yes.
I don't think I have it. I got through 46, and then the next one I got is 51.
Yeah, actually, 1 second. I'll send you.
All right.
Actually, since I understand this, we can move on to the other group of problems, and I'll send it to you.
Okay. I do see an interesting problem right there. What's the question for 51?
I actually don't have that on the quiz yet. We're doing that next week.
Okay. All right. So where do you want us to go to next?
About to send it to you right now.
Okay. Holler when it says sent. And then usually
Okay.
it's like 2 seconds. It's like 2 seconds after that it gets to me. Huh? 10 seconds maybe?
I guess so.
I still haven't gotten it.
I'll send it one more time.
No, I got it. I got it. I got it. It was like 15 seconds after you said sent.
Okay.
I got to learn to be more patient, I guess. All right. Which one's here?
1 through 12. So actually, we'll just do number 1 and then 3 to,
Okay.
I guess, as far as we can go within the time.
All right. These tend to be pretty easy where you're reading the graphs.
Yeah, basic graphing.
There's a trick to it, and once you learn the trick, they're all pretty much the same. Okay? So what's the limit of f of x as x approaches 2?
0.
What's b?
So -3 from the plus side, that would be -2.
c?
C will be 2.
d?
Does not exist.
e?
0 from the plus, -1.
Okay, you know these down pat.
Yep.
How about h?
Would that be infinity?
No, remember, look at what f of x is doing as
Okay.
x goes to infinity.
Oh, it looks like it's at 1.
Yeah, you can't actually tell for sure from this drawing. In other words, it's possible that there's not a horizontal asymptote at y equal 1. In other words, if I were to draw the natural log function, looks like this. Almost looks like there's a horizontal asymptote there. But if I said, what if this function is y equal log of x, and I said, what happens as x goes to infinity? What happens to y?
It would just stop.
No, it goes to infinity.
Keep going. Okay, so it keeps going up.
Going up, yeah. This is an extremely flat function. I think I've probably told you before that you have to go 2 miles to the right in order to go 12 inches up. So when you look at this graph on the right, it looks a lot like there's a horizontal asymptote there. And it would be tempting from the graph to say that it approaches that horizontal asymptote, but it does not. So you cannot always tell from the graph. In other words, who's to say that this part of the graph on the right isn't like a log function where it keeps just increasing, it's just very, very slowly. So I'm not sure that we can say for certain that the limit of f of x is 1 as x goes to infinity. It sure looks like it, but looking like it and being it aren't always the same. But I'm sure the answer they're looking for is 1 on H. How about I? as we go to negative infinity?
Okay.
What's the function go to?
That would be 0.
Yeah. Well, you understand these good. That's good. All right. Where do we want to go now? 3 or 2? We need
3.
2 is just going to be a repeat of 1, right?
Yes.
With a different function. So should we go
Correct.
to 3?
Yeah, 3 works.
All right. Yeah, there's no point in going over stuff that you know really well. All right. Now there's something else about x going to infinity or negative infinity. That's end behavior. Remember when you studied end behavior?
It's been a while, so
Well,
I need to
end
reflect.
behavior is, let's take this function here. Y equals 1 over x minus 1.
Okay.
That's hyperbolic, shifted 1 unit to the right. So it has a vertical asymptote there, and it still has the horizontal asymptote on the y-axis. And if I draw it, it looks like this. And if I were to say what happens to the function as x goes to positive infinity, you're looking at the horizontal asymptote, right?
Yes.
That's what happens to y as x goes to positive infinity. Y goes to 0. And as x goes to negative infinity, y goes to 0. So when x goes to positive or negative infinity, it's the same as what are the horizontal asymptotes, and it's the same as what is the end behavior. Okay, well this first one is y equal 2 over x minus 3. Well, notice that's hyperbolic, only there's a shift down of 3 units, so there's the horizontal asymptote at minus 3. My vertical asymptote is at 0. Draw the hyperbolic function in that grid. You get something like this. Now tell me what happens as x goes to positive infinity. What's y go to?
It goes to negative infinity.
Oh, look at the graph.
Or no, -3.
Okay, good. What happens as x goes to negative infinity?
Goes to asymptote.
Goes to -3 also. In other words, the end behavior is the same number on right and left for this particular function. They both go to -3 as x goes to infinity. And the reason is that that thing goes to 0, right? As x goes to either positive or negative infinity, and you were to take the limit of 2 over x, well, that whole thing's going to go to 0, which leaves the -3 as your answer. So we don't have to necessarily solve these graphically like I've been doing. We can solve them algebraically. In other words, just take the limit of 2 over x. As x gets really big, either in negative territory or positive territory, this whole thing goes to 0, and that's what you want to know.
Okay.
Okay?
Let's put a 0 in for that.
No, that thing goes to -3. In other words, the answer to 3 is -3.
But would I put the 0 in for x?
You don't put 0 in for x, you put in infinity.
Okay.
In other words, there's a big difference. 2 over infinity is 0. 2 over 0 is pretty much infinity. Notice the difference. It's huge. 0 is a long ways away from infinity. And this is a problem that a lot of people, They don't know how to divide by 0. Most people want to divide by 0 and get 0. Well, you don't get, when you're dividing by something very, very small, you get an answer that's very, very large.
That makes sense.
All right, let's look at number 4. Pi minus 2 over x squared. If that's equal to y, well, the best way to do these is to just substitute infinity.
Okay.
Positive and negative. Okay.
So infinity squared.
So what's y go to when x goes to positive infinity?
So I'd plug in positive infinity and x, and that'd be 2 over positive infinity squared.
Okay.
So would that just be 0?
Yeah, that's the key thing. Always remember that if you have a number divided by infinity, it's going to 0. The only time it's not is if you have 0 over 0. Remember, that's where limits are hard. Limits are easy when you have a number over infinity or you have infinity over a number. In other words, it's not hard to figure out what those go to. So it goes to pi, in other words, as x goes to positive infinity. What does it go to as x goes to negative infinity?
It would just be pi as well.
Correct. All right, the next one. 1 over, in fact, these are actually easier to do algebraically than they are graphically.
I'm noticing that.
What does this go to as x goes to infinity?
1 over 2, 1/2.
And how about negative infinity?
1/2.
Okay.
That's pretty easy.
Yeah, it's real easy once you get the hang of it. What's this go to as x goes to positive infinity?
0.
No.
So it'd be 1 over 8.
This part goes to 0. But the rest of it goes to 1/8.
Correct.
Right? You see why?
Yes.
Nothing about
little
the 1 or the 8. It's only this part here that I got the arrow coming out of that goes to 0. And then what's it go to as x goes to negative infinity?
1/8.
They're going to give us a hard one here eventually. These certainly aren't hard. Whenever you're dividing by x and x is going to infinity, well, you pretty much know what that thing's going to go to, right? So
Yes.
Positive infinity, what's it go to?
Negative 5 over 3.
Negative infinity, what's it go to?
Negative 5 over 3.
Yeah, you'd think they would give us one that doesn't go to the same exact thing for positive and negative infinity, but so far we haven't seen it.
11 and 12 look difficult, somewhat.
Okay, let's look at some trig functions, because, yeah, I think you got the hang of this. In fact,
Actually, don't worry about it. I actually booked another appointment at 7 o'clock your time.
oh, tonight?
Yes.
Okay. Make sure.
So I'll see you then.
Yeah, it did. Okay, so we got a half hour there. Oh,
Yep.
We only had a half hour scheduled here.
Yep.
Yeah, I was thinking we had an hour. Thanks for reminding me. I would, because I got another appointment at 4:30 and I would have totally been late for it. So
No problem.
we'll finish these up later tonight.
Yes, sounds good. Thank you.
Bye-bye.
Bye.